Hi, this is Paul Gregg. I'm going to talk about what I did for spaghetti properties and some testing and things like that. I wanted to start off with what I consider the a diagram that shows what structural development, and a lot of engineering is this way. You start out with the requirements, and that's very important to figure out what you're really trying to do. And then you make up a design or a lot of designs, and then you go through this four-step cycle: design, fabrication, test, and analysis. And in grade school and high school, a lot of times they skip the analysis because they don't have enough math background to do it effectively. But that's really what a lot of a college education is traditionally, that you learn how to analyze things with equations and methods. But you can, and people started out this way. They didn't know analysis. They do design and fabrication and test. And you can do a really good job if you design and fabricate and test, especially with things that don't cost very much, like a spaghetti tower that we're talking about. You can design it, you can fabricate it, you can test it, and then you can design it again, and you can go through this cycle of design, fabrication, and test. And that's a great way to do it. But when you get to something big, a big building or a roller coaster or an airplane or a ship, you can't afford to design it, fabricate it, test it, and then figure out what you could do better and do it again. So analysis is a way of modeling real life with mathematics, and that helps you. So what a real engineering, the best kind of engineering, has all of these components. You start with the requirements, you make some designs, you go to analysis, and you go back and forth. So you don't have to build anything. Once you start building things, things start to cost a lot. Generally, not in our little world of high school where we build aluminum foil boats and things like that. You can just go right to the fabrication and testing, and you can do that. So, but you have a bunch of designs in mind, and then you analyze and maybe tweak it and analyze and go back and forth. Then you go start building things. Now, this says element and subcomponent hardware because you don't have to build the whole airplane. You can build a wing, and that's a subcomponent of an airplane. And even smaller than that, you can build a joint in a wing, something you know is going to be critical, and you can build a bunch of joints and test them. And you can design them, fabricate them, test them, and then analyze them and kind of go around this circle a couple of times till you get really good at even the smallest element levels and subcomponent levels. And you start out small and build up. So what this does for you, you design and go to analysis back and forth a bit. Then you start fabricating things, and you don't have to fabricate the whole thing or a subcomponent or generally just a element level test. Uh, and then you fabricate it. Now, and then you do NDI, non-destructive inspection and testing. And then you see the results of that, and you come back and you say, how did that compare to my analysis? Did this behave the way I predicted or not? And then you can use that to refine and iterate your analysis. So, and then you go back and you do a new design or tweak the design or something. If you go through this cycle a few times, you get really good. Now, the output of this is very good because if the more things I design, I can produce design guides, which tells the engineers in a company how to design something. Fabrication, I'm generally working with processes that may not be fully developed. And so I can develop my manufacturing processes and come out with process specifications. Okay, that's a deliverable. And that comes from this learning from this cycle. In the NDI and test world, I learn how to non-destructively inspect these element, subcomponent, and component level tests, and I refine my inspection methods and the testing methods that are going to result in a certification plan, which is what testing do I have to do so I can fly this airplane safely? And that's your certification plan analysis. Down here, you use that and you develop your analysis methods, which tells analytical engineers how to analyze the design and of every component of a like an airplane. You know how to analyze it. So that's the cycle of development that I like to present. And yeah, you can get a lot from just designing and fabricating and testing back and forth, but the analysis is really where you can save a ton of money because and get your design good in the first place. So today I'm talking about spaghetti material properties testing. And I made a video about the spaghetti tower acceleration table testing, but this is more of a component level of that. I test each piece of it. And because of the nature of the spaghetti, buckling is a big deal. They're long, skinny members, and when they get in compression, they bend sideways, and that's buckling. And you can calculate and test what that load is, and then if you know the loads in each member of your tower, which you can do by analysis, you can ahead of time, ahead of building and testing, you can beef those up and get a better design without uh, fabrication and testing. In spaghetti towers, it's not very expensive to build them and test them. But if it was a real building, it would be very expensive to build it and test it. And if it wasn't optimum, um, you need the analysis to make it streamlined and optimum and without as much fabrication and test. You really only get to build a building one time. And so there's a buckling test. This is a 3-point bend test of spaghetti, and then this is a tension test, where I'll go into the details of it. I won't cover all of the testing in this video. I'll make some follow-on videos which cover the testing. So basically, when you have a new material or a material you're unfamiliar with, you need to either look in the publications or build yourself a database of. You need to characterize the material, and this is how you do it. All materials have a compression strength, a tension strength, and a shear strength, and that's kind of what these pictures look like. Um, Torsion is kind of an extension of shear, and bending is an extension of both compression, shear, and tension. It's not quite as useful a lot of times, the bending test, because it's not the pure compression, tension, shear properties. It's a combination of those things, and sometimes it can be difficult to but it's a great test for comparing different materials and stuff. And I'll go into it. So we need tests to test compression strength, uh, to test tension strength, and shear strength sometimes. In this case, we don't do shear test. The shear, if it's a short, if it's a 3-point bend test and it's short, you do get a pretty good shear number. But so bending, we will do bending tests. And we will do buckling tests. Now, buckling, if you have a long, skinny thing like a piece of spaghetti and you push on it, it'll hold a certain load, then all of a sudden it will start to bend out of plane a lot. And that's called buckling. And the shorter, this is the buckling equation is this, and I think I point somewhere to a derivation of this if you're interested. But basically, the buckling load equals pi squared times the E, the modulus, the stiffness of the material, times I, which is the area moment of inertia. And that may be new to you, but I'll talk about that. That's the moment of inertia, is basically the resistance to bending due to geometry. But the one variable here that you can change is the length. And that is an important variable because it's the reciprocal of length squared. Uh, the buckling load is a product of these numbers, which typically don't change for a given design. This is the number that can change. So what it says is when the length is half, if you support it halfway, then the length is half, which means the buckling load has gone up by half squared, or by 4 times. And if you change it by into a third of the length, then L squared is 9. And so it's not a linear factor. It's very important to, and this is why you'll find in your spaghetti towers, the more you support it in intermediate spots, the shorter you make the individual buckling um, of what a certain segment of your spaghetti. And that's why it's very important to support it in between. Or you can make the moment of inertia higher by bundling the spaghetti, but that's certainly a way to do it. And we'll talk about that. The other thing is joint strength. our spaghetti towers are 10 inches tall, but the platform has to be 12 inches tall. The only way you can do that is join pieces of spaghetti together. And how do you do that effectively? And so joint strength, we can do some element level testing on joints, and we can come up with whatever joints we want to come up with. We can build little ones, we can test them, and make sure that the joint strength will carry the load. So these are the kind of spaghetti I found. I use all the same glue sticks, this AdTech, but I had uh, Berea. They call it thick spaghetti, but it's really pretty thin. American Beauty spaghetti is cheaper than that, and then the Better Goods, which is a Walmart brand, I think. Bucatini is medium on the cost, but it is different, and I'll show you how that's different. This is the a cross section of the Better Goods spaghetti. It's actually a tube. It has a little hole in the middle of it, so it's quite a bit bigger in diameter than the other pieces of spaghetti, but it has a hole, and that is a good efficient use of the material because it increases the moment the stiffness, the bending stiffness of it, which is the moment of inertia. I'll show you how to talk about this more. So it's about a 3 millimeter diameter on the outside, and there's about a 1 millimeter hole in the middle. And the moment of inertia of that is in inches to the fourth. We'll talk about moment of inertia in a while, but it's just more resistant to bending, which is a good thing. It helps the buckling, it helps in bending, it helps in buckling, and we'll see that. This is the American Beauty spaghetti. It's solid and a smaller diameter. And this is the Berea. It's very similar to the American Beauty. It's smaller in diameter and solid. And this is the cost of them. You know, if you go buy it at all of these are buying them at Walmart, it's 12 cents an ounce. Better Goods, 9 cents an ounce, American Beauty, and 15 cents the Berea. And that's important because we need to keep track of costs. In anything you build, airplanes, bridges, buildings, cost is something you got to deal with. And you need to factor that in. So this is just a couple more pages here. This is very, uh, I guess, college level engineering, but you can understand it. Uh, when we characterize a material, we want to know how strong it is and how stiff it is. And so we typically, for a tension test, which is the simplest kind of test, you're just pulling on it until it breaks, until it starts to yield, starts to stretch, and then it breaks at some point. And this is how a typical, this is for a typical stress strain curve. So there's stress on the x-axis and strain on the y-axis. Stress is a measure of how much load it can take before it breaks. Strain is how much it stretches. Okay, and those are very important concepts. Um, so you pull on it, it goes up, and then there's this what we call the elastic region. This, if you pull on it and let it go, it goes back to zero. Pull on it and let it go, it goes back to zero. And that means it doesn't have any permanent set in it, permanent stretch. But if you pull it, keep pulling it to a higher load, what you usually end up with is you hit the yield stress and then the ultimate stress. Yield stress is where this is no longer a straight line. And so if you go to one of these points up here and come back, you won't be at zero strain anymore. It'll be permanently deformed. Generally, that's not a good thing in an airplane like because if you flew it and the wings bent up every time you hit a high load, that would be distorted and usually not a good thing. And most things you want to stay below that yield stress. You want it to return to its original shape. But it's nice to know that if you did have a really severe day and once in a lifetime of an airplane, somehow the loads got above yield and you did, but it wouldn't let go. It would keep flying. It may strain. It may go past the elastic limit. It may stretch permanently, but it would still fly back and land on the ground and be safe. And so it's a great thing to have strain capability in a material as well as high strength. Um, so that the slope of this line, which is the rise divided by the run, or y divided by x, or the stress divided by strain, that is the stiffness. The Young's modulus, or there's a couple of names for it, but that's how stiff a material is how steep this line is. So we'll see on the next page some comparison of the glue and spaghetti. Um, so you typically you do a tension test. It starts to neck down here. It starts to get thinner, and then it gets really thin and long, and that's where there's a lot of strain. Okay, and spaghetti only goes up here and breaks. It doesn't have this stretching capability, but the glue does have a stretching capability. So the next chart, I did find a chart online about the glue. This is EVA, and these are different kinds of hot glue. Okay, and you can see the strength is pretty low on them, but they stretch a lot. They have great strain capability. This means it could 1,000% means it stretched 10 times its original length and still didn't break. And so it's very tough, we call it. This over here, the red line imposed, is about where the spaghetti would be. It loads up. It's much stiffer than the glue, and then it just breaks. It doesn't have any plasticity. It doesn't stretch. And so this is roughly where spaghetti would be on a tension uh, stress strain curve. Um, Strength, this really is how much load it can take, but it's load per unit area. And so we do that because if you know the strength of a material in as a function divided by the area, the load it can carry divided by the area, then you've got every application covered. It's not just how much load it can take, you know how much stress it can take. Same with strain, how much it can strain, and that's just a percent. So the units of stress are pounds per square inch or newtons per square meter, which is a megapascal. Uh, well, it's a million pascals, but a pascal is a newton per meter squared. And a PSI, we call it pounds per square inch. That's a pound per square inch. Uh, and I apologize. Sometimes I switch back and forth between these units, and it makes it probably a little confusing, but that's the way America is. We haven't gone totally um, metric like we probably should have. Strain is inches per inch, so it really doesn't have units. It's unitless. And this means for a 10-inch part, this is stretched 100 inches. It's 1,000% strain. And usually the strains we're interested in are a lot smaller than that, but this is so in contrast, aluminum and steel are way stronger than spaghetti. We knew that. So spaghetti might go up to 30 megapascals. Uh, Aluminum and steel and titanium, they go up 250 to 1,100, over 1,000 megapascals. So they're way off this chart. Okay, and you'd expect that because they're structural materials and dry spaghetti is not. Uh, anyway, I think I covered that. So on the next video, we'll talk about tension strength, okay, and what I did to characterize that.